55 kilometers across open sea, 6.5 kilometers tunneled beneath it. This is the longest bridge and tunnel crossing ever built. The Pearl River Delta is one of the busiest shipping corridors on Earth. Container ships pass here every few minutes, bound for Hong Kong, Shenzhen, Guangzhou. Any structure built across this water must let them through, survive typhoons, resist earthquakes, and still last a century. Engineers begin not with steel but with charts. Survey vessels map the seabed meter by meter. Echo sounders probe the soft sediment. Wind, current, and salinity are logged across every season. The Pearl River carries silt downstream every day, and the seabed under this crossing is mostly soft clay, up to 50 meters deep before solid rock. The route must thread between two major shipping lanes and an airport flight path. Before the first pile is driven, the geometry of the entire link is already fixed. The crossing cannot be one continuous bridge. Container ships from the deepwater port need a clear channel, and that channel is too deep and too wide for any pier. So the route dives underwater for nearly 7 kilometers, then climbs back into the sky. To dive and climb, the engineers need two artificial islands, each one a transition point between bridge and tunnel. Building an island in open sea begins with a ring. Giant steel cylinders, 22 meters across, are driven vertically into the seabed, each weighing over 500 tons. 120 cylinders form the perimeter of each island. They lock together like a coin standing on its edge, defining the outline before any sand is poured. This technique compresses years of conventional reclamation into a few months. Inside the rings, the sea is about to be replaced by land. Once the rings are sealed, hopper dredgers pump sand from licensed offshore borrow areas into the enclosed space. The fill is carefully layered, compacted, and drained, because everything built on top will rest on this body of sand. Each island ends up around 100,000 square meters of new ground, raised 5 meters above sea level. The shape is not arbitrary. Each island narrows toward the tunnel portal and widens toward the bridge connection, so traffic can transition without sharp curves. Drainage trenches are cut along the perimeter. Service buildings are sketched into the master plan. Crucially, these islands must hold their shape against tidal scour for at least 120 years. Their edges are armored with rock and concrete blocks. Inside the rings, the artificial ground is now stable enough to host the most demanding part of the entire project. While the islands settle, the tunnel itself is built on shore. The undersea section is not bored. It is assembled from prefabricated boxes called immersed elements. Each element is a reinforced concrete tube, roughly 180 meters long, 38 meters wide, and 11 meters tall. Each one weighs around 75,000 tons. They are cast in a dedicated dry dock, one segment at a time, with double layers of waterproof membrane and dense steel reinforcement. Concrete recipes are tuned for low heat, low shrinkage, and 120-year design life in salt water. 33 of these elements will be needed, plus a final closure piece. When a segment is complete, the dry dock is flooded, the doors open, and the giant box floats out under its own buoyancy. It is towed slowly into the estuary, sealed at both ends, waiting to descend. Lowering each element is a single, irreversible operation. Two specialized pontoons clamp the segment between them and ballast it down through the water column. A pre-dredged trench runs along the seabed, lined with a precise bed of gravel laid by a robotic carrier. The element must land within centimeters of the previous one, at depths reaching nearly 50 meters, in currents shaped by tide and river outflow. Once the new element touches its partner, a rubber gasket compresses against the end face. The pocket of water between the two seal walls is pumped out, and atmospheric pressure on the outside of the joint clamps the elements together with thousands of tons of force. Divers verify the connection. Bulkheads are removed, and the corridor extends by another 180 meters. The seabed below is now hiding a continuous, watertight road. Away from the tunnel, the rest of the crossing is conventional bridge, only stretched to extraordinary length. The main viaduct rests on hundreds of concrete piers, founded on steel pipe piles driven deep into the seabed. The piles reach down through soft mud to firmer ground, sometimes more than 100 meters below sea level. Above the waterline, each pier is shaped to shed wave and wind force, narrowing toward the deck. Pier caps spread the load and provide a wide platform for the spans to come. Construction is sequenced from both ends toward the middle, so multiple crews work in parallel. Marine cranes mounted on jack-up platforms lift prefabricated reinforcement cages and concrete formwork directly into place. Where the seabed is soft, scour protection rings the base of each foundation. A skeleton of evenly spaced columns now reaches across the open water, waiting for the road. The deck does not grow span by span in place. It is built in chunks on land, then carried out and dropped onto the piers. Each segment is a hollow steel box, fabricated in a coastal yard, fitted with shear connectors, and topped later with a concrete riding surface. The largest segments weigh several thousand tons. Specialized lifting vessels carry one segment at a time between the piers, hover into position, and lower it onto bearings that allow the deck to expand and contract with temperature. Joints between segments are welded and post-tension. This method turns a marine construction problem into a series of factory tasks plus precise installation windows. Weather, tide, and shipping schedules dictate every lift. As segments lock together, the deck becomes a continuous ribbon of steel and concrete sweeping across the estuary, finally tying the artificial islands into the wider road network. 3 navigation channels still need to stay open for large ships. At each one, the standard viaduct is replaced by a cable-stayed span. Tall pylons rise more than 100 meters above the water, and steel cables fan down from them to support a longer, higher deck. Each of the 3 crossings is given a distinct pylon design, a deliberate choice, so each section has its own visual identity along the otherwise repeating bridge. The cables are tensioned in a precise sequence, balancing forces between deck, pylon, and foundations as each new strand is installed. A complete cable stay can carry several thousand tons, and adjustments of millimeters change how load travels through the structure. Beneath these spans, container ships continue to pass in both directions, unaware that the road overhead is being tuned, strand by strand, to the dynamics of wind, traffic, and time. With the structure closed, the crossing becomes a road. A waterproof membrane is rolled onto the steel deck. Layers of stone mastic asphalt follow, formulated to resist heat, salt, and constant heavy truck loading. Crews paint lane markings down a corridor longer than many city expressways. Steel barriers are bolted along the edges, designed to absorb the energy of a colliding truck without throwing it off the deck. Slim lighting poles are installed every few tens of meters, wired through ducts hidden inside the structure. At each artificial island, ramps curve gently down into the tunnel portals. Inside the tunnel, jet fans, fire detection, and emergency walkways take their final positions. Toll plazas and immigration buildings rise on both shores because 3 jurisdictions still meet here. Every system is tested individually, then together. From the air, the line on the water now looks finished. It almost is. The Hong Kong Zhuhai Macau crossing opens to traffic in 2018, after nearly 9 years of construction. A drive that once took several hours by road around the delta, or a long ferry ride across it, now takes well under an hour. The structure is engineered for a service life of 120 years to withstand strong typhoons and major earthquakes. It threads together 3 different legal systems, 3 currencies, and 3 driving conventions. Beneath it, ships continue on the same routes they always used. Above it, traffic moves in a thin, steady line between coastlines that geographically were never far apart. The hard part was never the distance. It was the seabed, the channels, the storms, and the requirement that nothing already working be interrupted. The crossing answers all of them. A road, in the end, that floats, dives, and rises again across the mouth of a river.